Welcome back to Math 432, Applied Combinatorics. I'm Professor Asaf. Today we're going to be talking about how to prove things for lots and lots of values of n at the same time. For example, I could have this nice algebraic statement that if I add up the numbers from 1 to n, I might as well have done n times n plus 1 over 2. Now you can see one thing to do is always a sanity check. This is going to be an integer, right? I'm adding up integers, I'm going to get an integer. I've divided by 2. I want to check that's going to be an integer. Well, either n or n plus 1 will be even. If one's even, the other, or if one's odd, the other will be even. So it's okay to divide it by 2. I'll get an integer. So this makes sense. We always want to do that sanity check. So suppose I asked you to prove this for, say, n equal 1, 2, 3, 4, and 5. Then what you might do is you might just start doing it. Okay, for n equal 1, what does the statement say? It says 1, that's the left-hand side, right? I add up the numbers 1 up to 1, so that's just 1, equals. N is 1, so here's just some basic practice with plugging into a formula. I'm going to get 2 over 2 is 1, yeah, okay, true. And now let's do it for n equal 2. Then I'm going to have 1 plus 2, that's the left-hand side. Is that the same as if I plug in n equal 2, so a 2 plus 1 divided by 2, well, you see the 2's cancel, and I get 1 plus 2 is 2 plus 1. Yep, that's the same. N equal 3. Now I'm starting to get bored. Whenever you're doing something like this by hand and you start to get bored, that's a big clue that maybe you should be doing mathematical induction. But we'll do it up to maybe 2 more cases. So this is going to be 3 plus 1 over 2. Now this is non-trivial, right? I have to add these up and get 6. And I see that 4, okay, 4 divided by 2 is 2. 3 times 2 is 6. Okay, so now this is the first case that's interesting. I'll call it interesting because it's not just blatantly obvious that the answer works out. You have to sort of do a little manipulation. Let's do one more case. Plus 4, and this is supposed to equal 4 times 4 plus 1 divided by 2. Okay, well this is going to be, well, previously we had 6, so now it's 10. And here I've got 4 times 5 is 20 divided by 2, which is 10. So it is true. I could keep going on like this, but what if I asked you to prove this, and I want to prove it for all n greater than or equal to 1. So what I'm doing here will never work, right? I'm never going to prove it for all n. I'm going to get bored at some point and stop. But mathematically, I need to prove it for all n. And that's done for us. The way we're going to do something like that is with the principle of mathematical induction. So we learned about the pigeonhole principle before. Here's another principle, and it's worth writing it down. This is the principle of mathematical induction. And here's how it works. I think about the number line, and being a combinatorialist, I'm always going to have it just have integers. I don't really mind about the other numbers. They're not so exciting to me. Okay, so what are we going to do? How do we prove something by mathematical induction? Well, at a high level, what I do is I first prove an easy case that I know how to do. For example, here I proved it was true for 1. This is called the base case. Now, generally speaking, your base case is going to be pretty easy to prove. You're going to pick some small number and it's just brute force, plug it in, it's obviously true. And what the interesting part of the induction is a step. And I'm going to prove that if it's true here, it's true there. So this isn't a statement about 1 or 2 or 3 or 4 or any of these. All of these little steps are the same conclusion. If it's true for n, then it's true for n plus 1. That's the principle of mathematical induction. So what I'm going to do is I'm going to say if it's true for n, then it's true for n plus 1. So maybe we're going to make this a little bit formal. And what does the principle of induction say? It says that you're going to have 2 parts. So we're going to take a statement, a mathematical statement, of course, which I'll call P of n. For this example, P of n is the statement that the numbers 1 plus 2 all the way up to plus n is equal to n times n plus 1 divided by 2. That's a statement. We can evaluate it as true or false. Okay, what you need to do is you need to do a base case. Prove P of 1. Sometimes we want to prove P of 0. Sometimes we want to prove P of 100. The point is start somewhere. You need to show this is true at some point. Okay, that's what we've done over here. And then you're going to do an inductive hypothesis. So here, a hypothesis means we get to assume something. So what we're going to do is assume P of n is true and prove P of n plus 1 is true. That is what this step is doing. If every time I know it's true for P of n, I can conclude that it's true for P of n plus 1, then I can say it's true for all integers because I start here with my base case. My base case says start here. And my induction says, now you can step and step and step and step. And I can always step. So I can continue stepping forever, which means I prove it for all n. So then you can conclude, then, based on this setup, P of n is true for all n greater than or equal to 1. Okay, that's the logic behind mathematical induction. We always have two parts. There is a base case where you say it's true for some value. Often that value is 1, sometimes the value is 0, sometimes it could be something else. Wherever it is, that's where your induction starts. Then you get to assume P of n is true and prove P of n plus 1 is true. I'm going to come back and finish this example rigorously and do the formal induction for it, but I'd like you to take a moment between videos and see if you can write out your own proof using formal induction that this statement is true. And then we'll be right back with a proof on the boards.